recording. Okay, awesome. Okay. All right, let me share my screen. And awesome. All right. Hi guys, I'm Manuel. I'll be going over the page replacement algorithms and the file system question that you guys will see on the exam. All right. So let's start. So I'll be going over first in, first out, least recently used, and optimal policy. So right. So we'll get started. So first in, first out. Hey, I know you guys probably seen this before, so I won't spend too much time on it. So first in, first out, right? Think of it as like a queue, right? So the page that has been in the memory the longest will be removed, right? Does that make any sense? Right? You guys able to see my screen? Everything is everything good?
Yes.
Awesome. Okay, so let's begin. Right, let's begin the first in, first out algorithm, right? So we're gonna first add 7 to our queue, right? Then we'll add 0 also, right? 7, 0. Right, then we'll add 1. But now, right, we have 2. We want to add 2 to our queue. But, right, the way it works, right? Like I said, the page that has been in the memory the longest will be removed, right? So we see that 7 was the longest page here. So we're gonna substitute it. So it will be 2, 0, 1, right? Right, and then we'll keep going. Right, so it's gonna be 2, 0, 1, right? Because 0 is already here, right? So now we have 3, right? So now we see we go on from 2, right? Since we changed 7, right? We go on to the next number, to the next cell, right? So it'll be 0. So we're going to change 0 to 3. So it's going to be 2, 3, 1, right? Any questions so far? How I got this? Right? Right? So then when we move on, right? So we see 0. So then we update 1, right? So it's going to be 2, 3, 0. But now we see we have 4, right? So now we go back to the top, right? So now we change 2 again. So it's going to be 4, oops, sorry. It's going to be 4, 3, 0, right? And then we see a 2 again, right? So we change 3. So it's going to be 4, 2, 0, right? Now we see 3 again. So we're going to update it. We're going to update 0. So it's going to be 4, 2, 3, right? And then we see another 0 here. So we're going to update it, right? So it's the first value, right? So we're going to update 4. So it's going to be 0, 2, 3. And then we see these values already here. So it's going to be 0, oops, 0, 2, 3, 0, 2, 3. Any questions on how I got this? Any confusion on anything? Leave it in the chat. No questions? All right. All right. Then I'll move on. I'll leave this problem for you guys to solve. Right. You can also use this for least recently used and optimal. Oh, yeah. So I'll answer the latest question. So the value is already there. We don't have to update it. Right. So we see here. So we see how 3 is already in our values. We don't have to update it, right? Because it's already here. And then the way the logic works, right? Just think of it as a queue, right? So you just add the values, right? So we just change, right? So we go from, right, we want to add 2, right? So we change the first number, right? So it's going to be 2, 0, 1. And then let's say we want to add back 3, right? Then we move down, right? And we change 0, right? So just keep repeating the process, right? It's like pretty self-explanatory. So it's like, just think of it as a queue, right? Any more questions? Let's see. Okay, no, it's all good. All right. If there's any more questions, then I'll go over least recently used. Awesome. Right. So like first in first out, least recently used is similar to first in first out, right? Same process. However, we're gonna substitute the value that was the longest page that we're gonna change, right? So in least recently used, we're gonna look into the past, right, and change that value. Right? It might sound um I might have phrased it weird, but we'll see it here in practice, right? So let's take a look. Right, so same format, right? So we're gonna add 7, 7, 0, right? 7, 0, 1. And then we go to 2, right? So now we're gonna look into the past and see which value we haven't used the most, right? So it's gonna be, if we look to the left, right? We see that we use 7. That was the latest value that we changed, right? So we're gonna update that, right? So now we get 2, 0, 1, right? Does anybody got any questions on how I got this or confused how I got this? Yeah, so right, for least recently used, right? If we want to add 2 to our queue, right? We're gonna look to the left, right? We're gonna look into the past and see which page we haven't used, right? Which page was used the least, right? So if we look, or right, we see that 7 is the farthest from 2, right? So we're gonna update it, right? So that's why we get 2, 0, 1, right? So then, right, we're gonna keep going, right? We see 0 is already in our queue, right? So we don't have to update it. 2, 0, 1. And then we see 3, right? And as look past, and we see that 1 is the farthest from 3. So we're going to update 1. So it's now going to be 2, 0, 3. Right? 0 is already here, so we don't have to update it. But now we see 4, and we see that, hold on, give me a sec. We see that, let me make sure. We see that 2 is the farthest one that we haven't used, right? So, right, because we see 0 is the closest, so it's 3. So 2 is the farthest, so we're going to update it. So it's going to be 4, 0, 3. Right. So now
I
we
have a
take
question.
yeah.
Sorry. For column F, when
Hmm.
you insert 3, why do you because to me it looks like 0 has been in there longer than 1.
Oh yeah. So we're replacing like the ones in front of farthest. So if you look here, right? So if you look here, we'll figure out the farthest from this value, right? So we see that right, 1 is the farthest from 3. So we just substitute that value. Right. So that's basically what we're doing here in least recently used. So we're looking
Oh,
to
I
the
see, because
left.
0 appears. Okay, I see.
Hmm.
Sorry.
Yeah. Okay, no worries. Right. So then we continue, right? So we want to update 2. So we just check and we see that 3 is the farthest, right? So we update that. So it'll be 4, 0, 2. Right. And then we move on to 3. We see that 0 is the farthest, right? So we update it. So it'll be 4, 3, 2. Do the same thing again. Right. We see that 4 is the farthest here. So we will update it. So it's going to be 0, 3, 2. And the values are already here in our queue. So we're just going to repeat that. Right. So 0, 3, 2. Awesome. Right. Has anybody got any questions how I got this? Or is confused? All right, no questions. Then we'll move on to the next of the page replacement algorithms. So now we'll be going over page replacement. Oops, sorry, not page replacement, optimal policy, sorry. Right? So unlike least recently used, optimal policy looks into the future, right? So we look to the right of the values, right? So least recently used, left, optimal, right? So if you're having trouble, if you have like any issues with least recently used, just know, there's no, so you just look to the left. Right? So optimal, right? We're gonna look into the right, into the future, and see which one is the farthest, right? Same process, right? So let's go to this, right? So it's gonna be 2, yep, there you go. It's gonna be 2, 3, 2, 3. So oops, so not going to have this. Okay, okay, there you go. Right, so then we get 2, 3, 1, right? But now we want to add 5, right? And so when we look into the future, right, we see we don't use 1 at all anymore, right? So then we can substitute that value. Right? So we're going to get 2, 3, 5, right? Then 2 is already here in our queue, so it's going to be 2, 3, 5. And now we want to update 4. We want to add 4. So we're going to look into the future, and we see that 2 is the farthest, right? So we can just update it. So it's going to be 4, 3, 5. Right? 5 is already here, so it's going to be 4, 3, 5. Right? 4, 3, 5. Right? Now we want to add 2, and we see, right, that we don't use 4, right? We see that we don't use 4 all the way back to F to G, right? So we're just going to update the value. So now we're left with 2, 3, 5, right? And 2 and 5 are already here in the queue. So we finished optimal policy. Yeah. Does anyone have any questions how I got this or confused on anything? Let's see, several people are typing. Let's see. Let's see. How do we know we update 4, not 3, and we got to 2? Let's see. Can you specify which column? You know, Rena, do you know which column you're referring to? Oh, I going to J. Yeah. Right. So isn't so optimal policy, right? Even though, right, it's almost similar to first in first out, right? It won't guarantee you the same answers as first in first out, right? Right. So, but duplicates matter. Let me see. That matters in least recently used. Yeah. Yeah. Pretty much. Right. Is there any more questions? Anybody wants to? Yeah. So right, let's go to LRU. Right. Right. Least recently used, right? We look into the past, right? So we look to the left. Right? So, right, this should be all similar, right? You just insert these values into the queue, right? So you get 7, 7, 0, 7, 0, 1, right? And here, right, we want to add 2 to the queue. So we just look to the left and see which value we don't use, like the last one that we used, and which was 7, right? So it's going to be 2. So I want to substitute 7 for 2. So it's going to be 2, 0, 1. Yeah, I'll share the doc once I'm done. I'll share the document once I'm done. Right? And then we see 0 again, right? So we don't need to update it because it's already here. So it's going to be 2, 0, 1. Now we see 3, so we look into the left, right? And we see that the last one was 1, right? So you repeat the process for all of them till you get up to the last value. Let's see. Is there any more questions? Anybody wants to go over something else?
Do you mind sharing the doc in the chat?
Yeah,
Email?
yeah. Mhm.
All right. All right. Awesome. Awesome.
I'll show that. All right. If there isn't any more questions, then I'll pass it on to Jason, who will go over clock policy and the scheduling algorithm. Yes. Yeah,
Yeah.
you.
Those. Yes. Those are the only three that will be on the extra credit. Yeah.
Mhm. I'll
Do-do-do.
pass it to you, Jason.
Ironically, we actually use the same set of numbers for clock policy. This is going to make things a lot easier too. Okay, let me share my screen. So, do. Can y'all see my screen? And also, y'all, can you see my screen too? So you
Yeah,
can record this part.
yeah, I can see your screen.
Okay, awesome. All right, so sorry that I'm not using Excel sheet, so it's going to be a little uglier, but it'll do, hopefully. But anyway, so all right. First of all, real quick, for the PA3, I know a lot of y'all try to ask me for a code review. I'm gonna try to go over them after this exam review is going to be completed. So just be a little patient on that because there's a couple of y'all that asked me for a code review. And I guess this is also a nice little signal for some of y'all would like to see a code review too. So if you want to DM me on that, feel free to do so. But anyway, so we're going to go over clock policy now, and feel free to stop me at any point because I know that a lot of you guys have a lot of questions on this. So I'm going to try to take a little bit of time on this, so I'll go a little slower. But anyway, so just like what Manuel said about the previous algorithms, basically you'll have to insert all of these pages into these slots as you go through them, right? But the only addition to clock policy is that you'll actually have this little janky little pointer that will point as you go through the algorithm. And then I nicely wrote here that a use bit is 1, and if it doesn't have a use bit, then it's 0. So you're going to have like a very similar format on your exam too. And yeah, so basically let's get started. So first things first, we're going to insert 7 normally, like how any other algorithm goes, right? And what will happen is that you'll have a use bit as soon as you insert something at first. Okay, I'm just going to label it at the top, so it's like something like that. So every time you insert something, it will always come with a use bit. And what will happen next is that you will need to move the pointer down to the next available spot. Okay, so the next one is going to be, so we're going to keep the 7 with a use bit, and then we're going to point the pointer down. Okay, and it's gonna, or excuse me, sorry. I should have probably not have that. Whoops. How do I erase this pointer thing? Okay, I'm just gonna get rid of this guy. Sorry, it's a little ugly, but okay. So it's gonna have 7 use bit, and it's gonna point the pointer down 1. Okay. So the next up is gonna insert 7 with a pointer, or sorry, 7 with a use bit, and then we're gonna have 0 with a use bit, and then we're gonna point the pointer down 1. Okay. And round robin style, so we're going to insert 1 at the bottom, so 7 the use bit, 0 with the use bit, and then 1 with the use bit, and then we're going to point the pointer all the way back up. Any questions so far? Because this is pretty simple so far. So you basically just replace if empty, and I wrote it right here as well. So if it's empty, you basically replace the page in there, and then you move the pointer down 1 or back up in this case. I'm going to open the chat on my phone as well so that if anyone likes to type in chat. Okay, perfect. All right, so now this is where things are going to get a little bit confusing. So how do we insert 2 in here? So first we look that 2 does not exist as any of these pages right now. So we need to find a way to replace 2 into this little fault. Okay, so I'm gonna write this separately. So I'm gonna have this pointer right here, 7 with a use bit, 0 with a use bit, and then 1 with a use bit. Okay, so the way that we replace the 2 in this little page fault is that we look for the number that does not have a use bit, meaning the use bit is 0. Okay, so the way that we even turn off a use bit is that we move the pointer down until it reaches 1 without a use bit. So the way that we would do this is that first, the pointer is pointing to 7 right now, right? And it has a use bit. So we'll turn off this use bit. We'll label it 0. And it will move this pointer down 1. So this is kind of like step 2, if you will. And then the next step is that, okay, so we're gonna look at the pointer now. And it still has a use bit on, so we need to turn this one off too. So we'll have 7 no use bit, 0 with a no use bit, and we're gonna point the pointer down 1 again. Okay, so now it's pointing to a use bit again, and then we're gonna repeat this process. So 7, 0, and then we're gonna turn off this use bit because it's still pointing to use bit, and the pointer is gonna go all the way back up. And like I mentioned earlier, so since the pointer is pointing to a no use bit right now, we can actually replace it because it is the use bit is 0 right now. So now we're allowed to replace this guy right here as 2. And remember that every time you replace something, it's going to come with a use bit. So 2 is going to get in here with a use bit now, and we need to move the pointer down 1. So this is kind of the final result, or sorry, excuse me. 0, and then this is going to be 1, 0. So this is going to be the final result after all of that. So we're going to write this in here. So 2 use bit, 0, no use bit. I know this looks super ugly. I'm so sorry. 0, no use bit, and then 1 with no use bit. And we'll put the pointer right there. Any questions about this part? Okay, because that was honestly the most confusing part about this. So if you guys all understand, then it's hopefully. Okay. So next, we're going to look at 0 now. So because 0 actually already exists between these three faults, right? Because 0 actually already exists in here. And it just so happens that this 0 actually does not have a use bit right now, right? Because the use bit is 0. So all we have to do is that instead of replacing anything, we just have to enable this use bit to 1, right? So all we have to do is say, okay, so 2, 1, keep the 2, 1, and then 0, and then just turn on this use bit because we're trying to replace this 0 right now. The pointer stays. The pointer actually doesn't move at all because it finds that 0 is already existing in default. So that's kind of the second condition, if you will. So again, if 0 already exists, right, in between these three numbers, and if it doesn't have a use bit, all you have to do is just enable it and do not move the pointer at all. Any questions about this part? Okay, no questions so far. That's great. Okay, so now we need to insert 3, and I'm gonna go ahead and just get rid of this. So I'm not taking too much space here. Does anyone need this part, by the way, or if you want me to keep this? Anybody? Okay. Can y'all hear me, by the way? Just want to make sure. Okay. I'm just gonna move this on the side then, I guess. So where's this little thing? Okay, so for this part right here, so we have 2 use bit, 0 use bit, and then we're gonna point to this guy, 1 with a no use bit, right? Okay, let me read the chat real quick. Whoops. Why is my phone doing this? Come on. Okay, awesome. So at this part, we need to insert 3, right? And again, because it's pointing to a use bit right now, what we have to do is that we have to turn off this use bit and then move the pointer down 1, right? So it's going to look something like this. It's going to say 2 use bit, and then we need to turn off this use bit to 0. And it's going to move the pointer down 1 to 1, 0. Okay? And now, because it's pointing to a no use bit now, and again, I wrote right here, right? Replace if the use bit is 0, right? So if the use bit is 0 right now, we can actually replace the 3 in there now. So what will happen is that 2 use bit, 0, no use bit, and then we're going to replace this guy with 3 with a use bit, and then we're going to point the pointer all the way back up. And that's it. That's all we need to do for replacing the 3 in this. So this is going to look like pointer 2 with a use bit, and then 0 with no use bit, and then 3 with a use bit, just like that. Any questions? And again, I apologize for the terrible handwriting. I'm doing my sorry about that. But anyway, so if no questions, so next we have a 0 to be replaced again. And again, since 0 actually already exists in default, right? And it doesn't have a use bit, all we have to do is just turn it on. So pointer 2 use bit, and then 0, which is all we have to do is turn it on, and 3 use bit. And that's it. That's all we have to do for 0. Okay, so next up, we need to replace 4. Okay, and since 4 does not exist, we have to repeat that whole process again. I'm not going to do that because you can just basically see it from here. And there's kind of a little clever trick that some of you guys might already know. But if all of them are use bit and you need to replace something new, then all you have to do is just turn all of them off and then move the pointer down 1. Okay, that's kind of a little trick. So you can just basically say, what's it called? So 4 with a use bit, and then move the pointer down, and then 0 with a no use bit, and then use bit. If you want me to demonstrate that, I can go through this whole process again, but that's kind of a little shortcut to do that. Does anyone want me to kind of demonstrate the whole thing? Okay, yes. I really hate this. You want me to do the whole thing? Okay, that's fine. So so at this part, we have pointer 2 use bit, 0 with a use bit, and then 3 with a use bit. So we need to insert 4 in here, right? So in here, again, we need to turn this thing off and then move the pointer down 1. So 0 with a use bit, 3 with a use bit. And then since this is a use bit still, we need to turn this thing off and then we need to point it down. So 3 with a use bit. Again, it's pointing to a use bit again, so we need to turn it off. And then we're gonna point the pointer all the way back up. And then lastly, because it's pointing to a no use bit now, we can actually replace the 4 in here. So we can say that 4 with a use bit now, and then just point the pointer down one, just like that. 0 with a no use bit, and then 3 with the no use bit. And voila, there you go. So now we can just safely write this in here. So 4 with a use bit, 0 with a no use bit pointer right here, and then 3 with a no use bit. Any questions about this part? Oh my gosh. Yeah, any questions about this part? Okay, if not, so now we need to replace 2, and since 2 does not exist, we need to actually replace this. So it's pointing to a no use bit right now, and we could just simply replace 2 in there, right? So 4 use bit, so 2 is going to come right in here. Move the pointer down one, of course. Okay. And now when that 3 actually already exists, right? 3 actually exists right here, and it doesn't have a use bit right now. So all we have to do is we just need to turn it on, right? So 4 use bit, 2 use bit, and then 3 is going to get turned on, and the pointer does not move. So again, if it already exists and it does not have a use bit, all we have to do is turn it on. That's it. Don't move the pointer. Okay, and then right here, I'm just gonna do the whole process for 0 again. I'm gonna get rid of this. I'm gonna move this guy all the way there. And okay, brush. Okay, here we go. So we're gonna write this process right here. So 4 use bit, 2 use bit, 3 use bit, and then we're gonna keep the pointer right there. Now we need to insert 0. Right, so same process. It's pointing to a use bit right now. We need to turn it off, and then we need to point the pointer back up, right? So 4 use bit, and the pointer is going to be right here. 2 is going to have the use bit, and then 3 is going to get turned off. Okay, here we go. Turn off. Okay, so because it's pointing to a use bit right now, we need to turn this thing off. So 4 is going to get, okay, Jesus Christ. 4, 0, pointed down 1, so 2 pointer, or 2 use bit, excuse me, and then 3 without a use bit. Okay, it's still pointing to a use bit right now, so we need to turn this thing off as well. And 2 is going to have a no use bit, and we're going to point the pointer down to 3. So it's going to find that, now 3 does not have a use bit, right? So we can actually safely replace this with 0 now. So we can add this 0 guy in here with a use bit. So we can just basically turn this on, right? As soon as you replace it, and then point the pointer all the way back up. Oh, I'm lagging, sorry. Point it to 4. Okay. Any questions about this? No use bit, 2 with a no use bit, 0 with a use bit, and of course, point the pointer to 4. I see a lot of you trying to type in chat, but if you have any questions, feel free to speak up or type in chat, I guess. Yeah. For the first 3, why doesn't the 0 have a use bit? Like this one right here? Wait, I'm so confused. For the first 3, why doesn't the 0 have a use bit? Oh, wait, I'm trying to even, this one? Or the 6th one? 1, 2, 3, 4, 5, 6. No, this one has a use bit. Or actually, excuse me, sorry. This one, oh, okay, yeah, great question. So, okay, I see. Can I move this out the way? No, I cannot. Let me move this guy a little bit to the right. So this was kind of the process that I explained about for this step right here. But so basically, so in this condition right now, we have, so I'm going to kind of label this a little bit better. So right here is exactly what's happening right here. Okay. So we have the condition right now, like I kind of explicitly here, right? So 2 use bit, 0 use bit, and a 1 with a no use bit. So right now we need to replace 3 uh, in this column or in this buffer, right? Like you mentioned. So it's pointing to 0 with a use bit right now, right? So because it's pointing to 0 with a use bit, we need to turn this use bit off, and then we need to move the pointer down 1. Does that kind of make sense to you? So again, because the fact that like this is a use bit right now, yeah, we need to turn it off, and then we need to move the pointer down 1. And now because it finds that, okay, so now it's pointing to 1 with a no use bit, right? So now we can actually safely replace this with 3 and then point the pointer all the way back up. So that's kind of the whole reason for that. Yeah. Okay, so moving on, right here, so stuff right now, we have 4 with a no use bit, and we need to replace 3, right? So 3 does not exist in the buffer, so therefore we can just kind of replace this with 3 with the use bit, point the pointer down 1, so 2, 0, and then 0, 1. Okay, and since 2 already exists, and it, you know, it doesn't have a use bit, all we have to do is just turn it on. That's it. Turn it on, keep the pointer, 0 with an use bit, just like that. To write this a little bit prettier. There you go. And that's it. That's pretty much it for clock policy. So in a nutshell, whenever you replace something, point the pointer down 1, and then add it with the use bit, right? And if it happens so that there's no available slot, then you need to turn it off, move the pointer down 1, and keep on doing that until you reach to something that does not have a use bit, right? Like we mentioned in these processes. And then of course there's a special condition that if what you're trying to replace already exists and it doesn't have a use bit, then all you have to do is turn it on and keep the pointer. So those are the only 3 conditions as we kind of went through them. Okay? Any questions? Because in my opinion, this is like the hardest thing, like in my opinion. I don't know. I struggled a lot with this at first too.
So question, sir, are we going to do this one, like the whole process as a test, or we're just going to do part of it?
So what you will be asked is like you just have to you can just use a paper to like show your work or something, but yeah, you do have to actually punch in all the numbers and then the use bit. That's really all you have to do. But you don't even have to show the pointer. Rincon does not care. Yeah.
Okay, I see. Thank you, sir.
But I will say without the pointer, you're not going to get this question right. So yeah. Okay. Time control is pretty good. It's only 5:30 right now. So if there's no more questions, I'm going to go in and skip to all the scheduling algorithms. So I'm going to switch my screen to that. Hang on.
I had a quick clarification.
Mm-hmm.
So whenever you're inserting a number that already exists, you're just updating the use bit, but I see that the pointer is already on it. So suppose there's like a scenario where the pointer isn't on that number, can you still just update the use bit, or does the pointer need to be there for you to be able to update it?
Yeah, so very good question, right? So here's sort of like some of the examples. Let's say you have 2, 0, 1, 1, 3, 0, something like this, right? And let's say we're trying to let's say the pointer is like right here, right? It doesn't matter where the pointer is. Like let's say if we're trying to replace 2, okay, that's what we're trying to replace within this thing right here. All we have to do is just enable this use bit, right, to 1, and then keep the pointer. It does not matter where the pointer is. Does that kind of clarify for you?
Yeah, thank you.
Yeah, of course. Yeah, so let's say if there's a, so for colon 6, shouldn't it be 2, 3, 1? No. Okay, so once again, so going back to this little thing right here. Okay, so again, so it's pointing to 0 with a use bit right now, right? at this step right now. I like where I put the red rectangular box right here, right? So it's pointed at 0 with a use bit, and we need to turn this thing off. So it's turned off right here. So it's 0 with a non-use bit now, right? And we point the pointer down 1. So now we're checking at the pointer position at 1 right now, okay? And since 1 doesn't have a use bit, it's at 0. That means it's safe to be replaced, right? And that's why we're able to replace the 3 in here. And now it's written in 3 with a use bit and a pointer back up. So that's why the 3 is right here instead of the second one. Correct, yes. That's one way to think about it, yeah. So every time you flip off the use bit from 1 to 0, you need to move the pointer down 1. This is like 100%. You have to move the pointer down, yes. So another, I guess like another kind of a or let me actually answer some of the questions first. So the only situation where the pointer doesn't move when you change the bit from 0 to 1. Yeah, so the only situation again is when you, yes, when you replace something that already exists, right? So let's say like, for example, at this step right now, like 2 already exists, right? It's already in here and it doesn't have a use bit. So all we have to do is just turn it on and then keep the pointer. Yeah, that's the only scenario that the pointer does not change. Yes. The one we get tomorrow would not be on the exam, like when we did bankers on extra, we got. I'm confused. I'm trying to read this question around. The one we get tomorrow will not be on the, like when we did bankers on extra credit, we got that. Oh yeah. So okay, I guess what you're asking, if I'm understanding this correctly, is like you're asking if the clock policy is going to be on the extra credit. I answered in the chat that I said no. So this will not be on your extra credit, but it will definitely be on your exam. So please do study this for an exam. Yeah. Will we be asked about faults? No. No, you will not. Assuming we have to. I don't know what that means. But I guess like one more special scenario. So let's just say like 1 use bit, 2, I don't know, non use bit. It's not really special. It's still abiding all the rules, but I just want to show it. So let's say if we're trying to replace 1 right now. Okay, just let's say we're trying to replace 1, right? So notice how it's pointing to 1 with a use bit right now. Okay. Now, so if this is again, so if this is like not a use bit, is all you have to enable it and then don't even move the pointer. That's it. That's all you have to do. But because this has a use bit, it's a little bit more special, right? So what you do need to do is that you actually have to turn this off, and then you move the pointer down. Okay, and then repeat this process until you go all the way back up and then enable it, and then go and then move the pointer again. So you'll literally pretend that, I mean, this example will not be like on the exam. I don't think it will. Like this is such a special condition, but you'll still need to redo like all the steps that we did right here. But honestly, I don't think that condition will like it really will not be. Yeah, if Rincon even decides to do that, it's too evil. Sorry, I meant like whatever page replacement we get tomorrow, say first in first out, is what we get on extra credit. Oh, I see. It can be on both. I do not have a certain answer for you for that. So just study all. That's what I will say. And it's actually pretty likely that it will be on both, like both the extra credit and the exam. So for a mixing situation, we need to clear all the ones to reach the safe situation. Are you talking about the one that I just did here? Honestly, I don't even know why.
No, yeah.
Just honestly, just completely disregard what I said. Like, this will not be on the exam. If that situation happens, like it will not be on the exam. Honestly.
This one, so the one will be easier, like just like inserting the ones into 0, or just I think that's it. Like in the exam, we just like do the replace, like the updating the use bit from 0 to 1.
Mm-hmm.
Okay.
Yes, exactly. Yeah. Mm-hmm. So for the extra credit tomorrow, it will be either. Yeah. So all I can say is that the extra credit will not complete the clock policy. That's all I will say. For the sake of time, there's still so many more algorithms I have to go over. I'll go over that last, Switty. So I'll pin your message for now. If the time allows. How do I pin your message? Okay, I'll just copy this. Don't worry about it. I'll go over this last. Yeah. Okay. So any other questions about clock policy before I go into the schedule? Because the time is cutting a little short now. It's a cute dog. Okay. Anyway, so I'm gonna change it to the algorithms guide. Okay, so real quick, I'm gonna upload something in the chat so that you guys can use this to kind of follow along. Actually, I've already posted it way earlier, so I can just kind of. Okay. Copy message link. Yeah. So please go to that message and use this document. And before I kind of use this thing, you will be allowed to use Excel sheet on your exam, unless Rincon says otherwise. I really highly doubt that he's gonna be a bum about that. So you can use this Excel sheet on your exam. But yeah, I'm gonna give everyone a little bit of time to download this. Yep, exactly. Yeah, so you can use this on the exam then. Yeah. Okay, so there's 5 algorithms that we do need to go. Can you guys see my screen for this Excel sheet? Yes, no, maybe so. Okay, awesome. Perfect. Okay, so I'm gonna save round robin for last, just because it's probably gonna be the most time-consuming one. So first we're gonna do first come first serve, and then we're gonna jump to the other ones, and then we'll come back to round robin. So that's the order we're gonna do today. Okay. So first, for first come first serve, just like how this mentions, it's relatively simple. And oh yeah, I'm gonna go in and really quickly explain what these variables are real quick. So this is a scheduling algorithm, and all it essentially does is that it performs an optimized solution to try to schedule all these arrival times according to the amount of time that they need to serve. So as fancy as this sounds, essentially all it's doing is that it's just queuing up, and it's using different algorithms to try to queue all these processes. That's all it's doing. Okay, so the arrival time tells you, well, the time that it arrives, okay, in the queue. And the service time is how long it has to serve for that process. So for first come, first serve, all we have to do is essentially just, well, first come, first serve. So A comes first, and it's going to have a service time of 5. So what I'm going to do is I'm going to drag this. I'm just going to make it like a pretty color. I'm going to make it blue in this case. Okay, and it's going to serve 5 times. Okay, and then next, since B comes next, right, first come, first serve, and it has a service time of 2, so then we're going to serve 2. C is going to arrive next. C is going to have a service time of 3, so we're going to serve 3. Okay, and then D is going to serve 1, and then E is going to serve 4 times, just like so. So first come, first serve, super simple. Everybody just lines up in the, and whoever needs to arrive first arrives first, and whoever needs to be served first serves first. That's literally it. Okay, so the final time, or the finish time, excuse me, right, just indicates which time the process actually finishes. So for time A, the very last time that it needs to finish is at time 5. So we're going to put the number right here. Okay, and then for process B, it finishes at 7. Okay, so that's why this Excel sheet is very, very helpful. So it lets you know exactly like what numbers you're looking for. C finishes at time 10. So we're just going to put the number here. 11, or sorry, excuse me, D is going to finish at time 11. And E is going to finish at last at 15. So that's how you get the finish times. Okay. And on your exam, you're going to be asked for this number as well. So this will be actually nicely already calculated for you on the Excel sheet. But basically how this thing actually works is pretty simple. all it's doing is that it's just taking the finish time and then subtract by the arrival time. That's all it's doing. So for this case, like if you look at B, this is basically saying 7 minus 2 gets you 5. 10 minus 3 gets you 7. 11 minus 6, and so on and so forth. That's it. Yeah, exactly. Yeah. Oh, yeah. Pretty simple. Anyway, so yeah, so that's how you get the turnaround time. Now, just for the sake of demonstrating, this is basically saying this is more like the nerdy like statistic kind of thing. You will not be asked about this on the exam, but this basically tells you the turnaround time over the service time, right? So if you actually look at how this number is being calculated, basically saying the turnaround time divided by the service time. 5 divided by 2 gets you 2.5. 7 divided by 3 gets you 2.33. And the reason that we're doing this is kind of like measure like kind of the proficiency of the algorithm, if that makes sense. So you'll actually need to calculate like the average of all these 5 numbers to get this number. And the closer that this gets to 1, the more ideal the algorithm. And again, this is not required on the exam. It's just kind of a more of a fact that you can know from this. Okay. But again, so the only like important things is these kind of 10 things right here. And you don't even have to draw this graph. It just helps you a lot to actually understand how you get these numbers. But these are the numbers that you do need to punch in for your exam 3. Yeah. Any questions about this? So super easy, first come, first serve. Pretty simple overall. Okay. If there's no questions, we're gonna go again. We're gonna skip round robin. Oh yeah, also the difference between a non-preemptive and a preemptive algorithm. So as nerdy as that sounds, basically it's saying that this has no interruption. Okay, meaning that the process needs to go through the entirety of the service time before it gets to the next one. So that's all it's saying. So for a preemptive algorithm, the process can be actually interrupted by another process. And we're gonna go through that in just a moment. But first, we're gonna go through shortest process next. So I'm just gonna write this a little more explicitly. Shortest process next, right? Okay, so shortest process next, pretty simple algorithm overall, basically hence the name that it sounds, right? So it's just saying that we need to pick the process that the shortest service time next. Okay, so I have the chart already pasted right here, so we don't have to kind of scroll back and forth. So A has an arrival time of 0 and of 5, so we need to run the entire thing. And since this is non-preemptive, we just run the whole thing. Okay, so now here is where it becomes a little bit tricky, right? So at time 5 right now, okay, how many processes has already actually arrived in the queue? Okay, so B has an arrival time of 2, so B actually has already arrived right here. Okay, it's waiting the queue for A to finish, right? C arrived at 3. Okay, and then D actually arrived right here, right, at time 5. Okay, hopefully that part makes sense. So the arrival time again is the time that it arrives, right? So at time 5, all of these 3 are actually already waiting in the queue. So we need to find which one has the shortest service time, right? So between B, C, and D, which one is the shortest service time? Well, it's D, right? So because D is 1, and 1 is the smallest between these 3. So then right now we need to run D first, because this is the shortest process next. Any questions about that part? And don't be afraid to like cut me off at any point. Like interrupt me. I love questions. Okay, so at time 6 now, after D is done, right? Because D only has 1 service time, right? So at time 7, only B and C are left in the queue, right? Why is B placed at 3 and not 2? Okay, I in my head I was just thinking like after 2, right? B arrives. Does that make sense? But I can also write it this way, I guess. It's if that's a little bit more clear. Yeah. But yeah, so however you want to understand it. So at time 2, like after the time 2 finishes is when B arrives. So I just kind of write it like after the 2, if that makes sense. But yeah. But anyway, so so at time 6, right? So 60 finishes. one to the number would be better. I mean, it's just like, I mean, then B gets introduced in the queue. That's how I understood it, but you know, it really doesn't matter. Like, as long as like, however this like makes sense to you, like whichever processor in the queue, you know, it really does not matter. But anyway, so at time 6, so time 6, where was I? Yeah, so only B and C are left in the queue, right? Because time or process E has not gone in the process yet, right? So right now between B and C, which one is shorter? Well, it's B, right? Because 2 is smaller than 3. So now we need to run B. Okay, so at this point, time 8, actually E gets introduced in the queue now, right? Because the process E has the arrival time at 8. So E is going to get in this queue, right? So at this time, every process is already in the queue now. And the only processor that has not ran yet is C and E, right? So between C and E. So between C and E, which one is shorter? That's C, right? Because 3 is smaller than 4. So we need to run 3, we need to run C next. And then lastly, we need to run the entirety of E, because E is the very remaining, or, whoops, get rid of this, yeah, because E only has 4 service time, yeah. Any questions about this part? So basically, you look for the arrival times, and then, you know, you introduce the processes when they need to be introduced in the queue, and then you look for the shortest service time next. And you'll run that, and then you keep going. What if E arrival time was also 4? You mean the service time or because I mean, if E arrives at 4, right, then so at time 4 you need to consider E into the queue as well. Yeah, so that will make the problem a little bit more challenging, but essentially you would just take care of like whatever is in the queue at that time, right? And then, I mean, so I guess like just to kind of like answer your question real quick. So if E has an arrival time of 4, so after A finishes, so we need to check all of these processes to see which one has the shortest one. And still the case would be D, because D has the shortest service time. Yeah, and then so it will literally run D, B, C, E again, actually, just because the fact that E actually has the longest service time. Yeah. What if E has serving time of 3? Then do you play C or E first? Very good question. So if, let's say, if hypothetically this is 3, right? Very good question. I actually wanted someone to point this out. So you will run this in lexicographical order. That's just a fancier way of saying alphabetical. So you would just run C first and then E first, or E after. Or in other words, it also, I think the other way to think about it is that whichever has the first arrival time goes first too. Yeah. So because C actually arrives before E, and since like when Rincon gives you the exam, like there's no way Rincon's gonna give you like these processes not in alphabetical order. So whichever way you think about it is correct. So you will run C first and then E. Yeah. So for this case, it will be 4. Yeah. But I think on the exam, all the service time is going to be different anyways, just so that it's not too confusing. I'm pretty sure it is. Yeah. But it could be not. I don't know. I'm not 100% sure about that. Yeah. Okay, so we're going to go over the finish time. Of course. Okay, so we're going to go over the finish time 5. And then B is going to finish at time 8, right? So a little trickier this time. Again, B finishes all the way at time 8. Okay, so C finishes at time 11, D finishes at time 6, and then E finishes at 15 again. Okay, and I'm just going to quickly explain this one last time. So the turnaround time is essentially so this number will be 5 minus 0. This number would be 8 minus 2, 11 minus 3, 6 minus 5, so on and so forth. aren't you supposed to put them on the? What do you mean? Aren't you supposed to put them on the one above shortest remaining time? I'm a little bit confused since we're doing shortest process next. Oh my gosh, you're a genius. Yes, thank you. Whoops. What happened here actually? But yes, you're absolutely correct. Whoops. Okay, let me put this right here. Whoops. I'm sorry about that. So I'm gonna actually get rid of. Gosh, I really hate this so much. Okay, I'm gonna get rid of this. Okay, sorry about that. Yes, you're absolutely correct. Yeah, I actually mixed up these two, but let me go ahead and copy and paste this and put it like up here instead. Okay, it didn't let me do that. Can I cut this? Okay, perfect. Yeah, so just to not get these two confused. Yeah, thank you for that. Okay, so we're gonna go over shortest remaining time next now. So this is gonna say, okay, let me actually move this up. Okay, so this says shortest remaining time. Not really familiar with Excel, so sorry about that. But anyway, so shortest remaining time, preemptive algorithm now, which means that the processes can be interrupted. Now this one is a little bit more confusing than the earlier one, so just be a little bit, or just bear with me for a second. Okay, so arrival time 0, so we need to insert A first, right? So service time is gonna run 5. We're gonna run this one at a time for now, just to make things not too confusing. So so service time is 5, and we need to serve 5 times, right? So we're gonna serve 1, 2, and right here is when B actually arrives. Okay, so I'm gonna just write this right here. So B arrives at time 2. And at this time, we need to consider all the processes in this queue that has the shortest remaining time left, and they need to run next. Okay, so let me rephrase that, right? So while we're running A, because A arrives first, right? So A is gonna finish time 1, time 2, and then B arrives at time 2. So at this point, we need to compare between A and B that has the shortest remaining serve time left. So right here, A has a A has a remaining time of 5 minus 2, right? Because it has already ran 2 times. So this has a remaining time of 3. Okay? And B hasn't really ran it. It just joined the queue. And B has a remaining time of 2, right? Because that's the service time that it has. So between A and B, which one has the shortest remaining time? Well, it would be B, right? So B is going to actually interrupt A, and B is going to start running right now. Does that make sense to everybody so far?
Which means that if like a process enter like when once executing, and then like the server like the memory will compare like which one have like more time
Yes.
left.
Yeah, exactly. So whichever one has the shortest remaining like service time left needs to run. So you will compare as you go. Exactly the right idea. Yeah. So okay, so moving on, B is going to start running right now, right? And B is going to run, and at this time, actually, I'm going to move this a little. How do I? Just so that I can insert like another. I'm going to put this top so now we have a little bit more space to work with. Okay, so at this time, at time 3 right now, C actually enters, right? And could you please mute your mic, please? Thank you. Whoever's doing that. Okay, so so at this time, C actually enters in the queue, right? So we need to compare that at this time. So A is going to have 3 left, right? And B is going to have 1 left, right? So I'm just going to write this. So A is equal to 3, and then B is equal to 2 minus 1, right? Because B actually has already ran once, which gets you 1, right? And then C also joins in here. And then C is going to have a service time of 3 when it enters. Okay? So right now, between these three, which one has the shortest remaining time? Well, it's still B, right? Because B only has one left to run. So B is gonna run and it's gonna finish. Okay, and at this time, right now, at this time, let me just kind of write this right here. So times 3, yeah. So at this time, we have A is equal to 3, and then C is equal. So between these two, which one has the shortest remaining time? Well, in this case, they're actually equal, right? But A actually arrived first, so we're gonna run A first. Okay, so A is gonna keep running, and it's gonna run once, and then, well, hang on, we gotta stop right now, right? So I know it's a lot of steps, but a little bit confusing right here. But right now, A has only 2 left because it has already ran again at this step. Like it has run one time, so 2 left, right? And then C has 3, and then at this time, D actually enters. Isn't this C running to A? Thank you. I appreciate it. I really appreciate that. Thank you. Thank you. Thank you. Yes. Sorry about that. So C is A is running. Sorry. Yes. Thank you so much. Okay. So A has 2 left, and then C has 3 left, right? And at this time, D actually enters in the queue because D has an arrival time of 5 and has a service time of 1. So in here, we need to say D is equal to 1. Okay, so between these three, which one has the shortest remaining time left? Well, it's D, right? So D needs to run right now. Okay, and at this time, right, D is already done. Like D only has one service. It makes things a lot easier, right? So this time, we just need to compare A and C now because E hasn't entered in yet. So between A and C, which one has the shortest remaining time left? Well, it's A, right? Because A is smaller than C. So we need to run A. So we run A once, twice, and then at time 8, this is where, so A actually is already done now. A is completely finished. So C is equal to 3 is still left, right? Because we still need to run C. And then E is equal to 4, right? Because E needs to enter at time 8. So at this point, which one has the shortest remaining time between these? Well, C has 3 left and E has 4 left. So we need to run C first. So C is going to run, C is going to run, and then C is going to run again. And then we're going to run the rest of E, right? Because E is the very last process to run. Any questions about this?
Can you explain why A less 6, 7, and 8?
Sorry, I can barely hear you. Can you speak up a little bit? Or you can type in chat if you want to, yeah. Why is 8, 6, 2, 8? Yeah, so again, I'm gonna, okay, I guess I'll write this a little differently. Okay, so at this time right now, right, D finishes, right? So at time 6, D finishes, right? So in this time, A is equal to 2 and then C is equal to 3. Oh, the only processes left in the queue is A and C at time 6, right? Because excuse me, because B and D are already done, and E hasn't entered in the queue yet. Yes, but then you also need to compare between. Yeah. So between these two, again, which one is the shortest remaining time? Well, A has 2 left, right? So that's why we run A. No, A was not finished yet. A is still not done because A has a service time of 5. Yeah, in total. Right? Yeah. That's why I'm keeping track of these numbers as I go. And it's kind of important to do that. Yeah. Yeah. Okay, so just to kind of finish things off, the finish time for A is at 8, right? Because that's the very last time that it gets done. And then B finishes at time 4, C finishes at time 11, D finishes at time 6, and then E finishes at time 15 once. Any questions on this? Just waiting for people to type in chat. Yeah. I want to try to get done on this before 6:30, so we have a little time for fair share, and then we'll talk about. Okay, if there's no questions, I will move on to my least favorite one out of them all. Math, called highest response ratio next. Yeah. Okay, so one of these formulas that you will need to know is so to calculate the ratio is equal to the wait time plus the service time divided by the service time. And I'll explain what this means in a second. Okay, so basically in a nutshell, this is a non-preemptive algorithm that actually process without any problems. So, kudos on that. But anyway, so I'm just gonna use, okay, I'm gonna put like right here. So we're still gonna use this part, right? So arrival time, service time right here. And A arrives first. Again, this is non-preemptive, so run the entire thing. So A is gonna arrive and it's gonna run 5 times. Okay? And at this time right now, you got a question? Okay, I'm gonna go and unmute you. Sorry about that. All right, so A runs the entirety of it, and now next at time 5, right? So what has actually arrived at time 5 by now? Well, so B has arrived at time 2, C has arrived at time 3, and D arrives at time 5. So at this time, B, C, and D arrives. Okay, so this is where the kind of the math comes in between these three, okay, or among these three, excuse me, is that you need to calculate the ratio for all of these processes, and you compare them for the highest one, and the highest one will run next. So to use this formula, the wait time is essentially the current time minus the arrival time, right? Hence waiting. So what is B's service time, right? Or excuse me, what is B's arrival time? It's at time 2, right? So right now it's at time 5. So I'm just gonna say B ratio is equal to. So again, right now the time is at 5, and the arrival time of B is at. Oh, excuse me, sorry about that. B arrived at time 2, right? And please mute your mic if that's okay. So 5 minus 2. I don't know who's doing that, but I'm trying to find it. Sorry about this. And the second time he got nominated, fuck that shit and didn't do it. Either did it twice, or you only did it once and it was a one and done. Now he got nominated over 9 times. It really just cooked, and you're a fan favorite. Sorry. You just love fucking with you. This guy. Sorry about that. Okay, so moving on. The wait time, the current time minus the arrival time, right, which is 2. And then the service time for B, it should be 2 as well, I'm pretty sure, right? Yeah, so the service time is 2. I'm just going to copy paste this so I'm not scrolling back. Sorry. Makes it so much easier. Whoops, don't do that. There we go. Okay. Okay, so yeah. So 5 minus 2 plus the service time for B, which is 2, right? And then divided by the service time, which is 2. Okay, and this will get you, so 5 minus 2, 3 plus 2, 5. So this will be 5 divided by 2, which is equal to 2.5. Okay. And then next, we need to also calculate C. C ratio is equal to. So the wait time is the current time, which is 5, right? Minus the arrival time, which is 3, plus the service time, which is 3, and then divided by 3, which is the service time. Okay. And this should get you 5 divided by 3, which is 5 divided by 3. Okay. All right, so now we need to do the ratio for D, right? So D ratio is equal to, I know it's really tedious, but at time 5, right? And a minus the arrival time for D, which is 5, right? Plus the service time, which is 1, divided by the service time, which is 1. This is 1. So now, after you're done with calculating all these, you have to compare for the highest one out of these 3. And between, or excuse me, among all these three ratios, which one is the highest? Well, it will be B ratio, right? 5/2 will be the highest. So after you do all of that, you realize that, okay, so B actually runs next. So B is going to run the service time of 2. Any questions about this part? Okay. All right. If not, so then we're going to move, someone's typing. Okay. Never mind. So so at time 7, E actually hasn't entered yet. So we're just going to need to calculate the ratio for C and D. Right? So at this time right now, B ratio, or excuse me, sorry, because B is already done, right? So C ratio is equal to the current time, which is 7, minus the arrival time, which is 2, plus the service time, which is also 2, divided by 2. Or sorry, I completely mixed this up. Whoops. C ratio, sorry about this. So C ratio, arrival time is 3, okay? Plus the service time, which is 3, and divided by 3. I can mix it up with B ratio. Sorry about that. Okay, so this will be equal to 7/3. And now we need to calculate the D ratio, which would be current time is 7, minus the arrival time, which is 5, plus the service time, which is 1, and then divided by 1. And this will be 2 plus 1, so this will be 3. Did I do that right? 2? Yeah, so that will be 3. So between these two, which one has the higher ratio? Well, it will be D, right? So D, sorry for this overlaying text right here, but D needs to run the entirety of it. So the service time will be like this. And at this time, unfortunately, E has to in the queue, right? Because time 8, E actually enters. So we need to calculate between C and E to compare which one has the higher ratio. So C ratio is going to equal to the current time, which is 8, minus the arrival time, which is 3, plus 3, divided by 3, which is equal to 8 divided by 3. And the E ratio is going to be, the arrival time is 8, right? So which is 8 minus 8, plus service time is just 4, and then divided by 4. So this will get you 1. So you see that C ratio is actually way bigger than E, because actually it has been waiting for a while, right? So it kind of makes sense. So C needs to run next, right? So C will have a service time of 3, and then E is going to run the entirety of it at the very end, just like that. Any questions about this? I'll just quickly finish off the finish time. So this is 5, B finishes at time 7, C finishes at time 11, D finishes at time 8, and then E. Okay. All right. Any questions about this part before I go to round robin? All right. If not, we're gonna attack the devil right here, which is one of the hardest ones out of these for sure. So which is the round robin one. Okay. So for the sake of this, since it's 6:12 right now, we should have a little bit of time. We're gonna do 2 examples. So one is going to be quantum 3, and we're also going to explain one that's quantum 2, just to make it a little bit more difficult. Okay, so in a nutshell, what this algorithm does, and first of all, the algorithm is preemptive, so the processes can be interrupted. And in a nutshell, the quantum essentially tells you the capacity that a process can run in one sitting. Okay, so what that essentially means is that, so let's say that process A has a service time of 5 right now, right? So that means that it can only run 3 before passing on to the next process, because that's the capacity that it can run at. Okay, so to begin, the arrival time is at 0. Right, so we need to run 3, okay, because that's the capacity they can run. And then at this time, so this is where it gets a little bit confusing, right? At time 2, B actually arrives. So I'm gonna put B right there. Okay, so we're not confused about that. So at time 3 right now, quantum has already reached its limit. So it's going to tell A, you need to stop. You need to give it to the next process. Okay? So at this point, B was already previously in the queue. Then you need to run, A gets added back into the queue. Okay? So A needs to get added to the back of the queue. And I'm just going to put this as like A for the remaining time of 2. Okay? But here's where it gets a little bit confusing. Okay? So at time 3 as well, C actually arrives. Okay, so we do actually need to insert C first. So I know I kind of explained that really poorly, but so again, at this time, C enters at the arrival time at 3. So C needs to go first, and then we're gonna put the A back into the queue, just like a round robin style. Does that kind of make sense to you? I know I explained like really horrible, but yeah. Okay, so at this time, if you look at the queue, right? So B actually enters in the queue first. So we need to run B now. So B is going to run through it. And because the service time is 2 and it's smaller than the quantum, so we can actually fit 2 in there. So no problem at all. That's fine. Okay? And at time 5, D actually enters in the queue. So we need to put it here so we can say C, A of 2 left, right? And then we're going to put D in the back of the queue. Okay? So at this time, C needs to run first now, right? Because C has been waiting in the queue first. And C has a service time of 3. And since 3 actually nicely fit the quantum, we can actually run the entirety of it. Since the fact that the service time of 3 is equal to the quantum, right? So C runs the entirety. And then at this time, E is going to get to the back of the queue because E enters at arrival time of 8. So right now the queue is going to say A of time 2, D enters, and then E enters. Okay? So at this time, in the queue, it gets round robin back to 8, right? So because A has been waiting for a while in the queue. So this time we need to run the entirety of 8 because it has 2 left, and 2 is smaller than the quantum, so you can run the entirety of it. Okay? Hopefully that part makes sense to you. Okay? So now at this time, at time 10, it will be just D and E in the queue, right? So this is now pretty simple now. So D just needs to run next, right, with a service time of 1, which is smaller than the quantum, so that's pretty nice. And then E is going to get ran. So technically, well, even though E is the only process next, like left, right? Just to explain this a little more explicitly, right? So technically, E would actually run 3 times because that's what the quantum can allow. So right here, E actually gets added back into the queue. Well, there's nobody's in the queue anymore, so E just gets added back, and it's going to run the remaining time again. So it just literally round robin itself, if that makes sense. And you're done. That's it for the round robin. Yeah. And you might be familiar with this term like round robin from, I don't know if you guys like taken data structures in this university, but you might be kind of familiar with that term before, but it's kind of a similar idea, if you will. So we're going to mark the finish time now. So A has a finish time of 10. That's when it finishes, right? And B is at 5, C is at 8, and D is at 11, and then E is at 15. Okay, any questions about this? Okay, so if not, I'm gonna show one more example. I'm gonna literally just copy. Okay, how am I gonna do this? I'm gonna copy this and I'll put it all the way at the. Oh gosh, please! What the heck just happened? Okay, I'm gonna put it like right here, and then I'm gonna just copy in this chart. Just put it all the way at the bottom. Something like this, yeah. Okay, so we're gonna do this exact same example. But we're gonna do the quantum is equal to 2 this time, just to make it a little bit harder. So that we can understand this a little bit easier. Or not easier, but just to solidify our understanding of this. Okay, here we go. Okay, so something like this. And don't worry, I will also post this updated Excel sheet in the group chat so everybody can see it too. Okay, so just to go over this example one more time. Finish time. Okay, who cares? Who cares about this? It's whatever. Okay, so get rid of this. Da, da, da. Okay, so if the quantum is equal to 2 now, so we're going to run A first, naturally, right? So we're going to run 2, right? Because that's what it can allow right now. And at time 2, B enters, right? Because that's what the arrival time of B is. So in here, B is going to enter the queue first, okay? And then we're going to add A back into the queue, round robin style, with a remaining time of 3, because that's how much is left, okay? And then at this time, since B is in the queue now first, right? So B needs to run the service time of 2. So we're going to run the entirety of 2. And then you'll notice that like in the middle of running B, like at time 3, C actually arrives. So I'm just going to put it right here. So A3 and then C enters. Okay. So at this time, A is going to go first, right? So A is going to round robin back. So it's going to run once and then hold on a second. Okay. At time 5, D actually enters, right? So we're going to add, we're going to put it at the bottom. So we're going to say A of 2 left and then C and then D. Okay. So A still needs to keep running, right? Because it has to keep going, reach twice. Okay. And then right now we need to stop. We need to stop because that's what the quantum can allow. Okay, so at this time, we're going to need to add A to the back of the queue. Okay, so C and then D, and then we're going to move A to the back of the queue because that's what the quantum can allow. Okay, so right here, C is in the first in the queue, so we're going to run C of service time of 3 now. And again, C can only allow quantum of 2, right? So, and it has a service time of 3. So we need to round robin it back. So we're going to run this twice. And then right here is where it gets a little bit confusing, right? So right here at arrival time 8, E arrives. Okay, so right here, D, A, and then E is going to get added right now, right? Because that's what the arrival time of E is. And then C is going to get round robin back into the queue with 1 left because it has ran 2 and the service time was 3. Am I going too fast? I don't know if I'm going too fast because no one's saying anything, so I don't know. Someone's typing, so I'm going to give it a second. Okay. All right, so moving on. So D is in the first in queue right now, right? So now we need to run D, and the service time is just 1, so we can fit that in the quantum nicely. Okay, so at this time, we're just going to have A of E and then C of 1 left. Okay, so A gets round robin back, and A is going to run once, and then nicely at this time, just E and C of 1 left. Okay, so E has a service time of 4. So we can only allow, again, we can only 2. So we can only run it twice. And then at this time, C is going to be first in queue, and an E of 2, 4 minus 2, gets round robin back into the queue. And then C is going to run once, and then E is going to run twice, just like that. And just to kind of specify this so it's not confusing, but E of 2 right now. So that will be the round robin for quantum 2. And I know this graph looks absolutely, but yes, that will be the answer for quantum 2. Yeah. So this will be 10. This will be, what would this be? B finishes at 4. C finishes at 13. D finishes at 9. And then E finishes at 15. Yeah. Is there any questions about this? And I know this is like a much harder example than the from the previous one, but this is just to show you like what a smaller quantum can do to you. Yeah. Any questions? No questions? I'm gonna set for like 1 more minute just so that we'll have a little bit of time before we go on to fair share and give you all a little bit of time to type in chat. Yeah. Yes, you will most likely get all of them on there. Yeah. So we just input finish times for the exam and attach work. That's correct. Yes, you just have to put the finish time and also the turnaround time as well. How many points is this question? Like 50? I have no idea. I want to say it's like 20 or 25%-ish. Has Rincon mentioned about the weightage for algos is versus? I believe he mentioned in class, but I did not go to class, so I wouldn't know. And also, I just read this question like, wait, we use Excel and paper? Yes, you're allowed to use this Excel sheet for the exam. Yes. Okay, my chat is like updating extremely slow. I don't know. I feel like I've missed like a couple questions. I'm so sorry about that. I don't get white 8 ran before D. Jay, did you have a question earlier about that, or do you want me? Because I don't know which algorithm you were referring to. Oh, okay, all right. Shouldn't D run before 8 again since D arrives at 5? SMK, which algorithm were you referring to? If you still want to clarification for that. Round robin. Okay. I believe it was talking about this then, just because of what the timestamp was. I don't know why my chat is not updating. Okay, shouldn't D run before 8 again? Okay, so when D arrives at time 5, I'm trying to look through this real quick. Okay. Okay, so run before A. Okay, so the reason that it would not do that, wait a minute, hang on. You might be right, actually. Give me a second. Sorry about this. Did I do this wrong? C, okay, C arrives at time 3, which is correct. And then you're actually, oh, you're so right. I'm so sorry about this. Yeah. Whoops, I made a mistake here. So at this time, awkward. I'm actually gonna get rid of this. I'm so sorry about this. Okay, let me get rid of that. Okay, we're gonna go back to this round robin question real. Okay. Definitely gonna put this in the editing for sure. Okay, so so like SMK actually mentioned, so at this time, at time 5, right? So just to go back to this real quick. So at time 5, D actually arrives, right? And wait a minute. Hang on. Give me 1 second. Sorry, even I'm a little bit. Let's see. A. Okay, so because C needs to, so C arrives at 3, which is great. And then 5 arrives, okay, so D is going to arrive at. Okay, no, I was right. Yeah. Okay, whoops. Okay, I was so right. The answer is, so the reason This is so confusing to explain. Um, at time 5, or okay, let's just go at time 4, just to slow this down, right? So at time 4 right now, what would be in the queue, right? Because A actually has already been into right now, so it needs to go back into the queue. Okay. So when okay. Oh, I hate round robin so much. Okay, we're gonna start at time 3. Just it's a little bit easier to. Okay, so at time 3, right? So again, the quantum is equal to 3, so A needs to be cut off right now. Okay, and at time 3, B is already in the queue because the arrival time B is in the queue, right? So when B gets in this queue right now, actually, right? C also needs to be inserted because the arrival. And at this time, A is already sitting in the back of the queue in a round robin style at time 3. Okay, because A got cut off. So let me repeat this one more time. At time B arrived at time 2, so it's already sitting in the queue. C is at arrival time 3, so C gets added back into the queue. And then A gets cut off because of the quantum being 3, and then A is going to be sitting in the back of the queue. Okay, so at time 3, all these things already happened, so that's why I marked it right here. Okay, I'm just going to make this red. Okay, that happened at time 3. So then at time 4, B is going to get ran first, sitting in the queue. Okay, it gets ran twice, right? Because that's what the service time is. And then at time 5 right now, D gets added back into the queue. I'm so sorry about that. Yeah. So because of the fact that A actually added D, do you see it now? Like right here, like what I marked. I'm gonna mark this like in a different color. Maybe like orange. I don't like that color at all. Just make it blue, I guess. Yeah. This is what happened at time 5. Yeah. Sorry about the SMK. I don't know. I just confused myself a lot. But yeah, so right now D will be added back into the queue, and A has been added a long time ago. Yeah. But definitely study all these scheduling algorithms. It's gonna be, I want to say it's like 25 to 30% of your grade, I think, at least. Yeah. But I don't know how many exact, honestly. I could ask Rincon on that actually. But yeah. Okay. Any questions on this? Okay, I'm gonna go ahead and save this document. What will be on the extra credit tomorrow? Again, it would be the page replacement algorithms, besides the clock policy one. So I'm gonna save that, and I'm gonna go ahead and change my screen to 2 of the smaller topics that you will see on your exam tomorrow. Okay, give me 1 second. Sorry, I'll open it up real quick. Fair share scheduling. Okay, here we go. Hopefully y'all can see my screen, but before I do that, I'm gonna go ahead and post this in the chat so you guys can look over this. Okay, so fair share scheduling. This is gonna be 100% on your exam, so I am allowed to say that, I'm pretty sure. So do definitely study for this one. Okay. Can y'all see my screen, by the way? Just want to make sure. I'm just, yes. Okay. Anyway, so so for this question, thank you. For this question, you're gonna be asked like a lot more of a simpler example than this one, given the PowerPoint slides. I'm pretty sure most of you guys have already seen this in your slides, but so what I'm gonna do is I'm gonna explain this more of a tougher one, and then I'm gonna move on to more of a like a side so that we will kind of go over both of them to see what you're gonna be expected to see on your exam. Okay. So just to really briefly explain the idea of fair share scheduling. So the whole idea is that you'll get 2 different groups of processes, and you want to fairly share them between those 2 groups so that each of them, runs based on their own priority. Okay, that's kind of the whole idea of fair share scheduling. And so in this case, you'll see that in the picture, it actually already identifies group 1 and group 2. into different processes, right? So process A is in group one. So let me just kind of zoom this out a little bit more. So process A is in group one, and then process B and C is in group two. Okay. Idea of oh my gosh, I hate this. Okay. So the idea of identifying them into groups is that only one group is allowed to run at a time. Okay. So if process A is running, then process B or process C will not be running. Okay. And if process B is running, then process A is not allowed to run at all. Okay, because process B is in group two. So on and so forth. So if process C is running, then process A. So that's the whole idea. So one group is allowed to run at a time. And whenever a group is running, the group CPU count is going to be running synchronously. So those are kind of the rules that you need to know. Okay. So if you take a look at the time zero right now, you'll see that these are the numbers that it starts with, right? 60, 0, 0, 60, 0, 0, blah, 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 blah. Okay. And if there's no like assumptions made or like nothing written explicitly about how many interrupts are allowed at one time, just assume it will be 60 interrupts per time. Okay. And I'll explain what this means in a second. Only one. That's absolutely correct. Yes, only one, and yes, only one process can. Yeah. Okay. So 60 interrupts per time. I'll explain what that means. But right now, so the very step when you solve this fair share, okay, you're going to be given what time zero of all these priority and the CPU counts is. Okay. So you'll be given like time zero, like something like 60, 0, 0, 60, 0, 0. Like this is literally the base template of the question. Okay. So what you'll do is that you'll look at the priority. Okay. I know it's a little bit blurry, but hopefully you guys can see. You'll identify all these priorities and you look for the lowest number priority. Okay. Now, in this case, they're actually all equal. So what you would do is that if it's all equal, you look at the lexicographical order, which means alphabetical order. It's just a fancy way of saying it. So which one is alphabetically first to run? Well, it'll be process A, right? Because A is in alphabetical order. Okay. So A is going to run 60 interrupts. Okay. It's going to run 60 interrupts for both the CPU counts, 60 times. Okay. And it's going to go on to time one. And I'm going to explain how these numbers come about. Okay. So when you go into time one, like after all interrupts are done, okay, you'll divide the CPU count by 2. Okay. So again, at first it starts at 0, right? So that's how you get 0 plus 60, which will get you 60. And then 60 divided by 2 will get you this 30. Okay, so again, this is 60. I'm going to write this a little bit smaller. Okay, so 60 divided by 2. 60 divided by 2. Okay, whoops. Yes, thank you. Thank you. I just didn't want to use that just because it's super complicated for no reason. But again, like how you get this divided by 2, 60 divided by 2, which is 30. Okay, and then now how you will calculate the updated priority is that you take the base priority. So the base priority is equal to 60, right? That's what the very starting priority is. And then you will use this base to add both of these numbers divided by 2 individually. So 60 divided by 30 divided by 2 plus 30 divided by 2. Not at all. No. Nope. Interrupt is not the same thing as priority. That's correct. Yes. So again, 60 plus 30 divided by 2, 90. And that's how this number is calculated. Any questions about this part? Okay, so technically speaking, you will actually need to repeat this process for everything here too. But because all of these are actually zeros, right? So you don't really need to do anything because they're not running at all. So like, 0 divided by 2 is 0. 0 divided by 2 is 0, right? And then this is just 60 plus 0 divided by 2 plus 0 divided by 2. So it's just 60. So in the same process here, right? So that's why they're kept the same there. Okay, so now at this time, I know there's a lot of numbers on the screen right now, but so that's essentially the whole process of calculating all these numbers. But then you'll repeat this process for every single time. So now you look at these priorities and you say, okay, between 90, 60, and 60, which one has the lowest number priority right now? Well, it will be 60, right? But because they're both equal, again, you will look at the alphabetical. So the alphabetical order says B runs first, right? So B is going to start running right now, as you can see blue right now, right? So it's going to run 60 and 60. So 0 plus 60 gets you 60, and then 0 plus 60 gets you 60, right? So you will repeat this process again, and then you will move on to time 2. So time 2 now, right? So 60 divided by 2. So again, I'm just going to write this here, right? So this is 60 divided by 2. And this is also 60 divided by 2. Okay, and then you'll repeat this process to calculate 90. Again, and again, you have to use the base priority. Okay, that's one of the biggest misconceptions that people get, is that you have to use the very first priority to add 30 divided by 2 and then 30 divided by 2, which will get you 90. Okay? Any questions about this? Like how these three numbers are specifically, right? Because we already did them here, right? So hopefully it's not too bad. Okay, so now you will look at the other processes. And so now you'll realize that, hey, like how did these numbers form, right? Well, even though they were not running, right? Because as you can see, like process B was the only guy that was actually running. This still needs to be calculated in terms of what the next priority is, right? Because the counts is actually not 0, right? So you'll still need to do this division from 30 divided by 2, which gets you 15 right here. So this is 30 divided by 2, right? You'll still need to do it, okay, the division. Just because it's not running doesn't mean that you okay? And again, like you ask like, hey, like how did the 74 come into play? Well, 74 is gotten from, so again, it will be the base priority, which is 60, right? Plus 15 divided by 2, and plus 15 divided by 2. And one rule for fair share scheduling is that there's no decimals. You have to use integer division, which means you round down. Okay? So this will get you 60 plus 7 plus 7, which is 74. And that's how this number is gotten. Sorry, it's like really blurry to see, but yeah. I cannot say. That's something that I cannot say. Yeah. But definitely do understand how to do like 2 process or even 4 processes. I do not know. Yeah, I cannot say about that. Okay, so that's how 74 is gotten. And then, so same thing right here, and then you're gonna, how is this 30, right? So again, like I mentioned earlier, whenever a group process is running, the group CPU must be incremented synchronously. That's what I said at the very beginning. So what that means is that if process B is running, right, in this group right now, like you see like at time 1, this is running, right? You'll notice that the group CPU count, this thing also needs to run as well. Okay, and that's why this is 60 right here, and this is how you got the 60 divided by 2. That's how you get this 30 right here. So again, this will be 60 divided by 2. And then the 75, I'm just going to write this on the side, the 75 base priority, which is 60, plus 0 divided by 2, plus 30 divided by 2, which is 75. And that's how this number is formed. I'm going to do one more time so that I'm not wasting too much time here, no pun intended. But so at time 3, okay, so after everything is done, you'll look at these priority, and between, I know there's, okay, so between 74, 90, and 75, I know it's like really hard to see, but which one is the lowest number priority, right? So it will be 74. 74, right? So 74 now needs to run. It needs to run 60 interrupts, right? So 15 plus 60 will get you 75. 15 plus 60 will get you 75, right? Because it needs to run 60 times. And then you're going to need to divide this by 2, which gets you 37. Again, must be integer divisions. So this is 75 divided by 2, which is 37. That's how you get this 37 right here. And same thing right here too. So 75 divided by 2. So 37. Okay? And how you get this 96? The base priority is 60. So 60 plus 37 divided by 2 plus 37 divided by 2, which should be 60 plus, I believe it's 18, right? Plus 18. And again, only integer divisions. So that's how you get this 96. And then you will repeat this process, so on and so forth for everything else. Yeah. Any questions about this? Okay, I'm not going to explain the rest because it's a little bit too time consuming. So I'm going to explain this one on, I believe this is on your practice exam, if I'm not wrong, but I'm just going to go over this one real quick. Okay, so again, this is what you'll be kind of given, right? You have the time 0, right? So in this case, again, this is 60 interrupts. And I believe, if I'm not wrong, like on your practice exam, this is like given, like it will say 60 interrupts per time, something like this, okay? So again, if it's 60 interrupts, so this 0 will need to run 60, okay? And what is 60 divided by 2? Well, it's going to be, I'm going to write this answers in red. Okay, so this will be 30, right? So this is going to run, oh yeah, and before I do that, sorry about that. So because the priority, right? So they're equal, so it's alphabetical order, so process A needs to run first. So sorry about that, okay? And so again, this will be, so this is going to run 60 times. I'm going to zoom in a little more so it's not too hard to write. So 60, and then this is going to be 30. Okay? And how do we calculate the updated priority? You take the base priority, which is 45, plus 30 divided by 2, 30 divided by 2, plus 30 divided by 2 again, which is equal to 15 plus 15 is 30, 30 plus 45, 75. So that's how you get this 70. That's how you get the 75 priority, right? Any questions how I got these three numbers? Okay, so because process A was running, process B will not be running. Each individual group cannot run, like it can only run one at a time, right? So this will carry, so this is 0 is not at all, so we're just going to carry this divided by 2 is equal to 0. This is also 0, right? And then we're going to keep this priority just because 45 plus 0 is equal to 45. Just to write it in red so that it looks a little better. Okay. All right, so at this time, we compare which one has the priority between. Well, it will be process B, right? Because process B has the lower priority. Okay, so now we need to run this thing 60 times. 60 times. Okay, and then this is going to be 60 divided by 2, which is 30. This is 60 divided by 2, which is 30. And then what is 45 plus 30 divided by 2 plus 30 divided by 2? Well, this is going to be 75. Oh. All right, so now, because this was not running, right? Because process B in group 2 is running, so process A would not be running. So we keep these 30, we keep these 30 as the counts, but then we also need to divide it by 2. So this will be 15, right? Because this is 30 divided by 2. 30 divided by 2, which is 15. Okay, and we take the base priority, which is 45, plus 15 divided by 2, plus 15 divided by 2. I know I'm writing on the box here, but who cares? Okay, so what would this be? This would be 45. And again, integer division, so plus 7, and then plus 7, right? And what would this be? 14, so this should be 59. And that's how you solve this. And that's pretty much it, because I think this is the only times that was required in this exam. But yeah. Any questions about this? Hopefully my chat is not bugged again. Give me a second. Just want to make sure. what if priority B was less? Well, it is less, right? Because 45 is smaller than 75 at time, then you will run process B first. Exactly. So very good question, right? So if this, like for example, if this was 40, if, right? So then you will run first. Run B first. Yeah. I know that's super ugly, but sorry. But hopefully you can understand it. Yeah. So then the numbers and at time 1 process A will be 40 exactly. So then you would just basically, right? So process B would then have 70, or not, it wouldn't be 75 then, right? Because you will actually, well, what would that be? Let me just do some mental math. 40 plus 30 plus 30, right? So it will be 100. Did I do that right? No. 40 plus 15 plus 15. So it'll be 70, 30, 30 here if this was 40, for example. Yeah, so the like if this in case, so this will be like 40, no, sorry, I don't know what I'm doing. 70, 30, 30, something like this, yeah. So let's just say if this was to be like 40, 0, 0, just for example. Yeah. And then A would stay as it is. It will be 45 in that case. Yeah. And then A would run next, right? Because A has a lower priority now, and it'll keep going. Yeah. All right. Any questions about this? I will have a little bit of time after the exam review. Also have to raise, right? If you have any questions about it, feel free to DM me. Just because time is kind of running short, I'm gonna hand it to Manuel to do one more topic, which is the file systems. So thank you guys for staying for this long. Yeah.
All right, thanks, Jason. So let me see. Let me share my screen. Yeah, good. Awesome. All right, here you go. All right, you guys see my screen? Let's see. All right, awesome. I'll send the link right here. Awesome. All right, so we will be getting a file system question. This will be on the exam. Okay. So let's just like break this down. Let's break this problem down. Right. Consider a file system with a block size equal to 4096 bytes, 1024 blocks for the first level of indirection, and in node format with 12 blocks for direct access, 1 block for single direct access, 1 block for double indirect access. Right. We have to figure out the number of blocks for the second level indirection, the number of bits in the file system, right? And to give recalling this as a hint, right? The size of an address, and the number of bytes in the direct level. Oh, hold on, let me change that. Sorry. Hold on. Okay, awesome. Okay. I just changed the. I think you should have access to the document now. Yeah, it should be good. All right, awesome. Right. So for this, right, you want to have this formula on your cheat sheet. Right. This will be super helpful. Right. So we want to figure out the number of blocks for the second level of indirection, right? Basically, this is just basically saying the second level of indirection is double the indirect block, right? So, right, and we already know 1 block for single indirect access, right? We know it's just, okay, sorry, let me make sure it should be, yeah, it should be, yeah, it's here on the cheat sheet, right? So it's just going to be the blocks, right? The number of blocks in one direct, right? And we know it's 1024 blocks. Right, so it's going to be 1024, right, squared, right, and that's just going to be, hold on, let me just do the math real quick. It should be, yeah, there you go, 1,048,576, right, that's what you will get here, right. Does anybody have any questions or on how I got this? No questions? Awesome. All right. And then now we'll move on to the second part of the question, the number of bits in the file system, right? So one thing to remember, right? A block is 4096 bytes, and it can store 1024 addresses, right? So we know, right, the size of each address is just, right, 4096 divided by 1024, right, is equal to 4 bytes. But the problem is asking for the number of bits, right? But we already know that 1 byte is equal to 8 bits, right? So we will multiply it by 8, and we will get 32 bits. Oops, yep, 32 bits. Right? If he was asking for a number of bytes, right, then it would just be 4 bytes. Right, so I would say for this problem, be careful on the units. Right, this is one of the, people really skip over, right? So make sure if he's asking for bytes, kilobytes, or anything, right, just make sure to pay attention to that small detail, right? So does anybody got like any questions? How I got this answer, or the previous one? Yep. No questions? Awesome. All right. And then for the number of bytes in the direct level, right? We know, right? The problem told us there is 12 blocks, right, for direct access, and each block, right? Oops, let me just, right? There are 12 blocks, and each block is 4096 bytes. Oops, sorry. Right. So all we have to do is, right, multiply the number of blocks, right, times the number of bytes, which is 4096, and we should end up with 49,000. Let me check. So times 96. Yeah, 49,152. Right. This is basically it, right? And this also is super powerful, right? This is also a similar problem in your practice exam, right? So I would advise also putting this on a cheat sheet, just so you can look over, right? Does anybody have any questions or confused on the problem? Let's see. Let's see. Someone's typing in the chat right now. Let's see. Yeah. We will publish the recording. I will just ask Jason where we'll put the recording.
I think I'm just gonna put it on the resources channel after recording gets buffered. Yeah.
All right.
But yeah.
Yeah. Any more questions, guys? On the question is asked for direct level capacity in kbyte. Oh yeah, in the practice exam, right? So it's kilobytes, right? So, right, we know, right, is this 12 blocks times 4, right, kbytes, right? So it's gonna be 48, right? If he was asking for bytes, right, then you'll multiply it by 1024, right? So here he asked for, right, number of bits, right? Oh, sorry, yeah, number of bits in the file system. So yeah, so units are really important here. So just pay attention, right? So just just pay attention to that small detail. But yeah, does anyone have any more questions? And yeah, I think that should be everything. Let's see. Someone is typing in a chat right now. I'm seeing Mac file. Oh, this is just what's it called? Extra stuff, right? This is like this, you won't see this on exam. Like I don't think Rincon will go. He will probably go up to double indirect, but this is just beyond that. Like he won't ask you this. Up to triple indirect, yeah, he won't go for that far. Yeah, no worries, no worries. Yeah, he won't go this far. I don't think so, at least. He's not that mean. But yeah, thank you guys for joining for the session. Let's see, I'll stop the recording.